what? One is a D1 equal to D2 equal to 0, right? That's one possibility, right? And if you do that, what happened? D1 equal to D2 equal to 0. That means our psi is equal to 0. That's a so-called trivial solution, right? And I think, okay, we still for this physical problem we have a solution instead of trivial solution. Okay, so here if you assume D1 D2 equal to 0, okay, you will get the phi equal to 0, which is trivial solution. Okay, it's not our solution. Okay, so the second case, okay, we can discuss if we assume the D2 equal to 0, what happened? But D1 is not equal to 0. Okay, so this is our equation, right? We just copy this equation, okay, to here. This is our equation. Okay, so that's our equation. Okay, so for second case here, we have a D2 equal to 0. So this term equal to 0. However, D1 will not equal to 0. Okay, so we have what? We have a, if D1 is not equal to 0, cosine 2 pi L over lambda should be equal to 0. Okay, so in order space pi, okay, is a for certain lambda n, okay, n is equal to 0 and 1 or 2, okay, for certain lambda n can satisfy this, okay, this formula here. There's a cosine for 2 pi L over lambda n is equal to 0, and we can have a 2 pi L over lambda n equal to what? Equal to 2n plus 1 times pi over 2. Okay, this is the only condition. When this condition is satisfied, our cosine of this will be equal to 0. Okay, so we can define the lambda n. Lambda n should be what? Should be 4L over 2 pi over from this equation here. So for this physical problem, okay, or for this physical solution, okay, we can do for the flow. For this flow, we only can have certain wavelengths can be sustained or can be survived inside this physical problem. Okay, as I say, if you want to satisfy this equation and then D2 is equal to 0, okay, and then this equation become like this, and this lambda n should be equal to this, otherwise they will not equal to 0. Okay, so when we have a certain lambda n, okay, should be satisfied this, and by using our dispersion relation. Okay, because the dispersion relation relate what? Relate our lambda wavelength to our wave speed. Okay, so we can find out any wavelength corresponding speed. Okay, wave speed, okay, by using this ratio. Okay, so this lambda n has to be specified at this location or this number here in order to satisfy our boundary condition. Okay, so we can construct the first solution look like, okay, if for this case, if a D2 equal to 0 and D1 is not equal to 0, okay, we should have this lambda n equal to this. So by using this, we can have the phi, okay, with a n mean a different, okay, number here. Okay, our solution set will be phi n, and phi n will be our constant become D1 n, right? This is a constant here, and our sign, okay, here. If we go back to here, here we have here, right? This is our solution look like, and we assume that D2 equals to 0, and when D2 equals to 0, our lambda only can have this, okay, should satisfy this formula here. So we apply lambda n into here, okay, and give us this sign of this. Okay, this is once we apply lambda n into here and times hypercosine here, and sine 2 pi ct, and over all the lambda here, we apply this, okay, formula into this solution form, we can get this. So this is one of possible solution. Okay, it's not trivial. So this is first. Okay, and then we have the third case. Okay, we may have the, instead of a D2 equal to 0, okay, we may have a D1 equal to 0. However, D2 is not equal to 0. What happened? So this is another case. We assume that D1 is equal to 0. However, D2 is different from 0. Okay? So according to our list, okay, boundary condition should satisfy this formula here. Okay, and then since D1 is equal to 0, so this is equal to 0. So our D2 is not equal to 0. So sine 2 pi L over lambda should be equal to 0. Okay, so here we can specify what kind of wave number here can cause our sine 2 pi L over lambda is equal to 0. And we define this lambda is called lambda m here. Okay, and lambda m should be satisfied this, right? 2 pi L over lambda m should be equal to m pi, because when sine m pi should be equal to 0, m is equal to 1, 2, 3, right? This is a number. Okay, so our lambda m can be written as by using this equation. Okay, can be written as 2L over m. What's the L? L is here. L is here, right? This is mass. This is L, 1/2 for this tank width. Okay, so our tank from this sidewall to this sidewall we have 2L. Okay, so we can construct another possible solution called the phi m. Right? This is related to this index m. Phi n is related to what? When D1 is equal to 0 and D2 is not equal to 0. So D2 is our only variable. This becomes D2m. Okay, and then so here we have the D1 equal to 0. So D2m cosine 2 pi x. Now the lambda already by using this formula can be into this equation here, solution form here. All the lambda is replaced by this. So we have this. Okay, so this is another possible solution. Okay, inside it for this physical problem. So as you can see, if you plot all the solution form, including this n, we have the previous we have n, right? Phi n. Okay, this is a possible solution form, and we have a phi n, another possible solution form. You plot that, as you can see, if you are phi n equal to 0, your waveform look like this. Okay. If your n equal to 1, your waveform will look like this. Steady wave waveform. If your m equal to 0, your waveform will look like this. Okay. If m equal to 1, your waveform will look like this. Okay. So all this is a possible solution for or satisfy what? Satisfy this flow. Okay. Once we have a rectangular tank, once you generate wave inside this tank, the possible solution, what kind of wave can be generated inside this rectangular tank? There's all kinds of, but they have common physical sense is what? All here is what? Satisfy our NP node. Here is NP node. Okay? NP node. NP node is what? NP node is, you remember, we have this picture here. NP node is here. Okay. And for NP node here, our particle path is moving in the vertical direction, so that will satisfy our boundary condition. Okay. So once we can have this, we can finally construct the final solution we have. We can superimpose these two actually. Okay, we have a phi n solution, right? This is a phi n, and then we have a phi m. Okay, phi m is this. And then you have a complete solution will be phi n d1n, d2m. Okay, there's a n and m has index from 0 to infinity, and we have these two sets, and you can superimpose by these two sets to construct all the possibility solution you have. Okay, for our physical problem. So this is the complete solution for our physical problem. Okay, and this is for this here. Okay, we should satisfy for this node here. We should satisfy this dispersion relation. For the D2m, this phi m here, we should satisfy this dispersion relation. So they are slightly different. Okay, so I think that will be the end story for this physical problem, I think. Okay, so this is a very complete solution. Okay, we can have. Okay. The last physical problem we have in the textbook is this. OK， 这是我们的所有的课程里面最后的一个章节。OK， so talking about we almost finished, right? So talking about the final exam, then you check. I think the final exam will be, the official final exam will be this day, right? 13. Okay, January 13. Okay, so just have final exam here. Okay. So that's our kind of this is final exam week. Okay, and I think that for 2-hour class is on Tuesday here. So remember, we don't have too much time. Right now it's almost here, right? Next week we may not. We only have a 1 hour class here. Okay, we may have a solution. Okay, homework solution to correct. Okay, maybe here or here, depending on. Okay, and then we have a 1 week here to see. Okay, any question you have? Okay, anyway. I hope I can finish as soon as possible and then allow you to study, okay, more, okay, and don't rush. So here is the last chapter, and this chapter is a kind of introduction to another course for hydrodynamics. There's one course, special course for hydrodynamics. Unfortunately, the lecture for this course just passed away, okay, last year or this year, okay. Professor Xiao Feibing. He usually teach this course, hydrodynamic stability course, every 2 years, okay. And then unfortunately, okay, maybe some professor may take over it, okay. And what's hydrodynamic instability course? Okay. There's a 2 book only actually. Okay. If you study hydrodynamic instability, only you can find only 2 textbooks. Hydrodynamic instability. Okay, let me see. Let me find a book. Where's a book? Anyway, I know the book, the author will be like this. Okay. Okay, and I forgot. Usually there are 2 textbooks, standard textbooks, okay. Maybe later, okay. And what hydrodynamic instability try to deliver to you? Okay, hydrodynamic instability is one of very special course. Okay, they try to using the control, okay, control concept into the flow system. What's the control concept? We have flow system like this. This is our flow system. Okay. And we would like to test this flow system is stable or unstable. Okay. And how do we test the system is stable or unstable from a control point of view? 你们控制组的，你们 any student from the control group? No? Or the flow mechanics group? For the control theory, you usually test this flow system by using input, a small perturbation. And try this is small perturbation into this flow system, and try to evaluate what happens if this small perturbation eventually become like this. So this is unstable. If it eventually become like this, this is stable. Okay, so that's the concept for the hydrogen instability. All the codes is talking about all kind of flow system, and we'll try to introduce the small disturbance inside this flow system, and try to study how this small perturbation or small disturbance will be end up with potential growth or potential decay. Okay, that's how we try to evaluate. Okay, and this chapter here is also kind of give you this kind of the concept, okay, to test a flow system, okay. So here is try to understand only one for this course we only introduce only one physical product, okay. It's a wave propagate between the interface. What's the interface here? What's the interface? Interface usually is very interesting. Okay, phenomena. All the interesting phenomena happen in the interface. Okay. For example, you have the two fluids with the different speed, right? And then you have and then we have the interface between that. Okay. Some flow is outlet here. We have the spring plate here, and some flow is upper interface. Sometimes we have a different density. Okay, with different density, with different, okay, instead of different speed. Okay, and try to see. Okay, for example, we have air flow here. We have water here. Right? Does it look like a free surface flow? Okay, and we have interface. Okay. And we can try to find out how the wave propagate along the interface, okay, along this direction. Okay. And we may have a superimpose, we have a density different, velocity different, okay, force. Okay. And so this will look like what? We have air flowing on the top of water, right? Air flowing, and then generate the surface wave. Right? You see that when you go to some beautiful lake, okay, wind is blowing, and then wave is generated on the surface. Okay? And all these kind of phenomena, okay, and then we start with it. Okay, so we try to study the so-called wave propagate at the interface. As you can see before, okay, the wave we generally is using so-called traveling wave, for example, A dot, right? A dot XT. Okay. Wait. Okay. You go back to like this. Okay. And go back to traveling wave solution. Traveling wave look like what's A dot should look like. Go back to origin of to specify a traveling wave. Yeah, this one, right? This 2 pi lambda. Okay, x mass ct. Okay, this is traveling wave. Okay, so we already assume, okay, this traveling wave is this kind of okay, with a specific wave speed, like this wave speed. Okay, and then in the one dimension sense. Okay, and how do you specify this kind of if you want to introduce a small perturbation into this? We also introduce a traveling wave look like flow. instead of using the X minus CT here, what we try to do here, we try to introduce a small perturbation on the free surface here. This A dot becomes like this, as you can see here. We go back to our retractor. Okay, the only difference is what? Only this C become what? C becomes sigma. Go here, okay, yeah, here. As you can see here, this is the okay. When you compare with this, our A dot for our study right now, A dot xt will equal to epsilon. Okay. Sine cosine function here, we instead of using the sine cosine function, and we're using its potential I, okay, and 2 pi x, 2 pi over lambda, okay, and x minus c, x minus, instead of ct here, we x minus sigma dt. Okay, erase this, you to see the difference. Okay, can you compare the difference here? And now using its potential function. Its potential function give you what? Give you the sine cosine function, right? Sine cosine. If this is I, and if inside here, okay, this sigma is may not be real number. Sigma equal to sigma r plus I sigma I. I use an imaginary number, okay, to represent okay, sigma here. Okay, and the A dot here is represented by this way. We call this normal mode analysis. Okay, in the hydrodynamic stability process, we introduce a small amplitude. This epsilon is very small amplitude. Okay, and my waveform will look like this. Quite similar to the traveling wave. As you can see, how similar. Okay, I can evaluate a little bit for you. Okay, if I extend this A dot xt, right, and epsilon is potential I 2 pi lambda x plus sigma is equal to sigma r plus I sigma I, right? So x minus sigma r what t, right? And then I plus equal 6, and then plus. Okay, here is plus 2 pi x, 2 pi over lambda. I written here much easier. Plus 2 pi over lambda. What? Sigma I, right? T minus sign. Is that right? And here this is real, right? This is C is also real. So this part is what? This part is real, right? This part is real. So this become what? This become, you know, this part is a cosine sine function, right? Cosine this. Okay, 2 pi plus sigma t plus I sine sine. Okay, so that's this part. This part represent this part. Okay, this is traveling wave. And the rest of part is this part, right? This part is we have its potential. This will be I here, right? And I is equal to what? Equal to minus 1 times this 1. This is minus sign to come from. So we have its potential. I times I equal to minus 1, and this is minus sign. So this potential 2 pi lambda sigma I t. Okay, we have one additional term here. So here is just like a traveling wave, right? This is similar to this is sine function by using the cosine sine function to more general only. Okay, this is just traveling wave. I introduce a small perturbation, traveling wave inside the flow system, and try to evaluate, try to see this, what happened to this. If the sigma I is greater than 0, what happens? When sigma I is greater than 0, this disturbance, small perturbation disturbance will be what? Will be its potential grows with time. That means unstable. Okay? Just have a picture, I have input like this into this flow system, right? And I try to see if this small perturbation become like this. if the sigma I greater than 0, that will become like this. Right? If the sigma I is less than 0, what happens? This potential decay with time. So this, when I have a small perturbation, okay, and then find out input into the flow system, and this flow system, finally I got this. I should check what happened to this sigma I. If this sigma I is identified as less than 0, that will be this flow. It's stable. So that's how I check the flow is stable or unstable by using this kind of normal mode analysis. Okay, I can introduce this small perturbation inside the flow field and try to test. Okay, try to test. Okay. So this is a very special, okay, waveform. I introduce this waveform and try to see. Once I introduce this waveform, A dot equal to this, into the flow system, right? Into the flow system. And into, what do I mean into the flow system? Into the flow system means you have to satisfy all the Gaussian equations you should have, all the boundary conditions you should have. That means into the flow system, right? So, once you introduce this small perturbation, okay, this is very key concept. Once I introduce this xt is equal to epsilon, okay, it's potential I if I over lambda, okay, x minus sigma t, something like that. If I remember correctly, yeah. Okay, into the flow system, right? So this is small perturbation I introduced into a flow system. This is flow system. This is our flow system. Okay? When I mean into the flow system, mathematically mean what? I have to satisfy for this flow system if I assume the boundary equation is the Laplace equation, and they have all kinds of boundary conditions, right? Boundary condition 1, boundary condition 2, boundary condition 3. Right? I have a dynamic boundary condition, I have a bottom or boundary condition, I have a free surface boundary, any kind of boundary condition I should satisfy. Once I introduce this small perturbation into this flow system, in order to satisfy this, and I will try to check what happened to the sigma I. Okay? That's the next method we will try to do that. Okay? And try to evaluate the sigma I. Okay? This is the imaginary part of this sigma. If this sigma I is greater than 0, this wave is the wave its potential growth with time. That's unstable. Okay. If this sigma I is less than 0, imaginary part of sigma is less than 0, my perturbation will be its potential decay with time. This flow will become stable. Okay? Got my point? Okay? Let's do that. Let's try one case. You will understand what I mean. Okay? So here is a perturbation we would like to introduce into the flow system. And as you remember, this is called a normal mode analysis. And why do you use the sine cosine function instead of a more complicated function? Here we only have the sine cosine function, right? Here the perturbation is the cosine sine function. Why do you introduce only sine cosine function? Why do not introduce more complicated function? 为什么？为什么我们用 sine cosine 会用到更复杂的波形去测试它？ Any student have comment for that? It's not true, right? You only use the sine cosine. In reality, there's more complicated wave, okay? Perturbation instead of sine cosine, so simple, right? Did my comment make sense or not? 为什么它只有用 sine cosine 方式这么简单的？为什么不用复杂一点的？复杂一点的不见得不符合啦。Remember, what's the Fourier series tell you? any arbitrary weight